Did anyone get it?
Good.
Give your attendance along with the roll number. Those who joined late, for them I'm saying. Okay, no issues. So clockwise currents I will take in loop 1 as well as loop 2. Okay, so you can write KVL in loop 1. Okay, so it's -2 minus 2I1 minus 3I1 is equal to 0. So this I'm taking I1 and this I'm taking I2. That implies I1 is equal to basically minus 2 by 5. That is equal to minus 0.4 amperes, right? Then you apply KVL in loop 2. So it's minus 3 I2 minus 4 minus 5I2 is equal to 0. That implies I2 is equal to minus 4 by 5 plus 3 is 8. Minus 4 by 8, that's negative 0.5 amperes. Next, what you do is you just reconstruct the network, okay, which is found between node X and Y. Okay, let's say this is A and let's say this is B. Okay, so just place the nodes something like this, X, and then comes A, and then comes B, and then comes Y. And now you just place the elements. Okay, between X and A, you have a 3 ohm resistor. And then you have a battery with the designated polarity. Okay, and then between B and Y, you have a third 3 ohm resistor. Okay, and across the node X and Y, you are supposed to find the potential. Let us assume it as Vx5. Okay, a battery having an unknown potential. Doesn't matter. Okay, just conveying the same meaning that you're trying to find the potential across node X and node Y. So that is being denoted by this unknown, this battery with an unknown potential Vxy. Okay, and we are moving in this direction, right? We are going from X to Y. So it is something like clockwise traversal. Okay, in the meantime, what you do is you had assumed the current directions, right? In the beginning to find out I1 and I2. Okay, so try to place those currents. The current is flowing. See, this I1 is flowing from X to Y. So, X to A, right? So put the current direction something like this. And top of it, you write it as I1. Similarly, in loop 2, current I2 is flowing, from bottom to top. Okay, so that is Y to B. So mark the current in this direction and name it as I2. Okay, correct? No, the current is flowing, see, like this. bottom to top. That is node Y to B. So that's what we have written here. Once that is done, you can apply KVL. So let's apply KVL in the clockwise direction. Clockwise direction. Okay. So first of all, the battery is traced from negative to positive, and then you have the drop, that is minus 3 into I1, and then you have a battery potential which is plus 4, and you see you are moving in clockwise direction, but I2 is flowing in the opposite direction, hence plus 3I2 is equal to 0, or Vxy is equal to 3I1 minus 4 minus 3I2, or Vxy is equal to 3 into what is I1 minus 0.4 minus 4 minus 3 into minus 0.5. Okay, so that gives you Vxy is equal to minus 1.2 minus 4 plus 1.5. Okay, and how much is it? Minus 3.7 volts. Okay, did you get it? Did you get
Yes,
the?
sir.
Yeah,
Yes, sir.
fine. Great. Fine. So that's how you solve. So any problems related to this particular network, if it is given, I'm very sure that you will be able to solve it. Okay, fine. So today let us talk about some different kinds of problems. Okay. So just note down. Find the current. Okay. Find the current. Find the currents in various branches. Find the currents in the various branches of the network shown below. Find the currents in the various branches of the network shown below. Okay, so this is your network. Okay. So this is the network. Okay. So this network is kind of, it resembles honeycomb structure, right? And you have been given with the details about various currents. Okay, some currents are entering, some currents are leaving, and also you have been given with the branch resistance. Okay, branch resistance, and the question is find the currents, okay, in the various branches of the network. Okay, so very important problem.
Excuse me, sir.
Yeah.
Someone's trying to join the class.
I know. The moment I start teaching, I find it very difficult to track them. Okay, but nobody is there. No, I have admitted. Nobody is
So,
there in the meeting room.
so she texted me saying that I'm not able to join the class.
Now I'm in the lobby window only. Nobody is here. Ask her to join once again.
Okay, sir.
What happens is that if the presenter won't allow them,
Okay, sir, she joined it.
she joined the work. Fine. All right. So this is the network. Now you're supposed to find the currents in various branches. Okay. Now how to begin with? How to begin with? Okay. First of all, observe that there are no voltage sources given in this particular network. So when you apply KVL, summation E becomes 0. Okay, remember summation E becomes 0. Okay, where summation E is sum of EMFs. Okay, that means to say the network is being powered by some other source, but that particular source is not shown in this particular network. Okay, now to solve this particular problem, what you have to do is that some unknown current you are supposed to consider. Okay, and that current you can consider, anywhere in this particular network. You can consider at this branch, or you can consider at this branch, or anywhere. Okay, so let's say I'm going to assume that unknown current where over here. Okay, say here I'm going to assume that current. Okay, and let me take that current as I. Okay, so this is how I start this particular network. And in the meantime, let me also mark, okay, name the nodes A, B, C, D, E, F, so that I'll be able to apply KCL at these nodes. Okay, now what I'll do, I'll start applying KCL, okay, one after the other. Say for example, okay, I will apply KCL at node B. Okay, let us apply KCL at node B. Now, at node B, what is that you are seeing? You are seeing that, you see, current is entering here. We have assumed, right? I in this particular direction. At the same node, 80 amps current is outgoing. Okay, and there should be some current flow from B to C as well. Okay, since the direction is not given, I will assume it in this particular direction. Okay, let's say clockwise direction, I will assume. Trust me, even if you take it in anti-clockwise direction, you will get the same answer. Okay, see, what you do is, I mean, presently you please follow what I do it on the board, and at home you try out with different current direction instead of outgoing. Perhaps you can even consider incoming. Okay, with that also, you'll be able to get the same current magnitude. Okay, that we will do it later. Now, this particular current, let me take it as IBC. So when I apply KCL at node B, what do I get? Incoming current is I, and outgoing current is 80, and I have the one more outgoing current, right? What is it? That I'll take it as IBC. Okay, but I do not want to keep current as IBC. I want to keep current IBC in terms of I and the known current, right? So IBC is equal to I minus 80. Okay, let's just highlight this particular equation. So what is the description of current that flows from node B to C? It is I minus 80. So let's write this as I minus 80. Done? Okay. Next, what you do, apply KCL at node C. And this is how we proceed. Okay, apply KCL at node C. So similarly, at node C, what I will do, I will assume current flow, something like it flows from node C to node D. Okay, so what do I have here? So when I apply KCL at node C, I have an incoming current. Let me write it as it is, which is IBC. Then I have second incoming current, which is 90 amperes. And then I have the outgoing current, which is I C to D, right? So I C D, let me write. But what is IBC? IBC is I minus 80 plus 90 is equal to ICD. Therefore, ICD is equal to I plus 10. Let us highlight this. I plus 10. Okay. Similarly, now let us apply KCL at node D. Apply KCL at node D. All right. And while applying, let me assume the current direction in clockwise. Okay. Say D to E, it flows. Now, when you apply KCL at D, you get something like this. Incoming current, that is ICD, outgoing current is equal to 150. Okay. And outgoing current, that is also, okay, what is it? Outgoing current, D to E, right? So it is IDE. Okay, and ICD description is known to you, that is I plus 10. Okay, and this 150, you bring it on to the left hand side. So this becomes minus 150, and that is equal to IDE, or IDE is equal to I minus 140 amperes. Okay. 140 amperes. Okay. Now let us apply KCL at, say, node E. Okay. And over here also, let us say this current is flowing. Okay. Okay, we will mark this current. Okay, ICD, how much did we get? I plus 10, right? Let me write I plus 10 here. Similarly, IDE, how much did we get? I minus 140, right? I minus 140, let us write. Okay, and let's find this particular current. Okay, that is IEF. So, can you help me with the KCL? What should be the KCL equation? Can you tell me? Anyone?
120 plus I minus 140 is equal to I of EF.
Great. 120 is incoming plus I minus 140, that is also incoming. And that is equal to the outgoing current, which is IEF. So when you simplify, you will get the description of IEF. And how much is it? IEF? I minus 20. Correct. Okay. So this current also you have obtained I minus 20. Okay. And then finally, I am left with, the KCL at node F. Okay. Since I have to scroll down, I'll not be able to see the figure. You'll have to help me out. Okay. So I'll write here KCL at node F. Okay, probably someone else can help me out. Okay, I'm not, I cannot see the figure. That's the reason you have to tell me. KCL at node F. Is there any incoming current at node F? If so,
I minus 20, sir.
okay, I minus 20, you're saying it is incoming.
Yes, sir.
Okay, and are there any outgoing currents?
80, sir.
Okay, is equal to outgoing, right? 80, and then?
Plus FE, IFE.
Okay, IFA, right?
Yes,
Yeah,
sir.
okay. So, thank you. So, IFA is equal to I minus 20 minus 80, or IFA is equal to I minus 100. I minus 100. Okay, so let us mark that current. So this is I minus 100. Okay, and the final step is to apply KCL at node A. So when you apply KCL at node A, the outgoing current should be I amperes, because that is what you have had assumed in the beginning, right? If you do not get IAB as I amperes, then somewhere you have made mistake while applying KCL. Okay, let's cross check. So finally, let us write apply KCL at node A. Okay. So someone else, you have to tell me. Okay, person from, say, from girl side, can you help me in applying KCL at node A?
Sir, IFA plus 100 equals to IAB.
IFA plus 100
100
equals
equals
to
to IAB.
IAB. All right. So what is IFA? IFA is I minus 100, right? From the previous step, IFA we have obtained as I minus 100 plus 100 is equal to IAB. So 100 gets cancelled. So is IAB equals to I? Is that so?
Yes, sir.
Correct. So that means to say we have successfully applied KCL. Okay. So this is the way we try to find out the various branch currents. Okay. All right. So that's the first task, to find out the various branch currents. Okay. But we haven't found the magnitudes of these branch currents. We have just written the equations. Okay. Now what we do is, in the second step, okay, in the second step, what we do is apply KVL in the closed loop. Okay, apply KVL in the closed loop. In the sense, what I'm trying to tell you is that you can, let's say, yeah, apply KVL in the closed loop, let's say in the clockwise direction. Okay. Apply KVL in the closed loop. Okay. So in bracket, let me write, we have chosen clockwise direction. CWD stands for clockwise direction. Okay. Fine. Can you tell me? Just go with the branch current. So let's start from current I. Okay. Let's start from current I. So I into the resistance. Okay. Then this I into resistance, this current into resistance, this current into resistance, so on and so forth. Okay. So let us start. So it is minus I into 0.02. So minus I minus I into 0.02. Next, what do I have? I minus 80.
80
Yeah, no,
into 0.02.
yeah, 0.02. okay, into I minus, I just have to, so many times I
I
have
plus
to,
10.
yeah,
I plus 10
scroll up and down. That may cause nuisance.
into 0.03.
Yeah, great. Yeah. Please go on. Okay, keep telling me. Then,
Minus I minus 140
okay,
into 0.02, sir.
okay, and
Minus I minus 120 into 0.01, sir.
is it 120 or
20,
1 second,
sir.
sir.
20?
20, sir. 2020, sorry, sir. 2020.
I don't recall getting 120. That's the reason I asked. Okay,
20,
yeah,
0.0.
right. And then minus I into, sorry,
100. Minus I 100 into 0.01.
0. That's it, right?
Yes, sir.
Is equal to 0. Okay, now it is little laborious work. You will have to, now what is unknown in this particular equation? You tell me. I is unknown, right? Then everywhere you have some, constants, 80, the resistance, etc., etc. So solve this equation to get current I. Okay, so just let me know how much you'll get it. Carefully how to solve. The moment you get it, please post your answers in the chat box. So I is nothing but IAB, right? Take your time. In the meantime, I'll just keep ready the branch currents. Then we have IBC, ICD, IDE, IEF, and I. That's it. Yeah, and EFA, right? Yeah, EFA is there. The writing is legible, right? Give me the feedback, okay, every day, because if it is not visible, please tell me. This is probably I minus 80. Yeah, then I plus 10. I minus 140. You have given me the current, so I can write it down. I minus 20, and this is I minus 100. Yeah, any luck? Did anyone get it?
So 30 amperes.
Okay. Put it in the chat box. Let me see. Let me see. Advik wants to join. Okay, let's admit him. Yeah, 48.18 should be the answer. Okay. Those who have got different answers, please check your addition. 48.18 ampere is the answer. Please check. Okay. See, once you get the answer as, answer for IAB, which is actually the unknown current I itself, right? Then all what is required is substituting that particular current in the different equations to get the current value. So this becomes I minus 48.18, and this becomes I plus 48.18. Sorry. This is 48.18. Okay. So let me start writing the current values. (48 minus 80), that's negative 31.82.
58.18
Positive, yeah, 58.18. This will be 91.82. Okay, how about this? It's a positive number.
28.18.
Superb. Then finally, negative number you get. Okay,
minus 51.82.
Minus 51.82.
82 amperes. Right. So this is how we solve this particular problem. Okay. Now, some currents are positive, some currents are negative, right? The negative current simply means that the assumed direction is opposite to that of the actual current flow. Okay, that's all. So don't worry about the direction, okay, because we cannot guess the direction with 100% accuracy. Okay, that's the reason the law itself states that algebraic sum of currents. So there is some sign convention, and when we take that sign convention properly, you will end up in getting the same magnitude. Of course, direction may change. Nobody will worry about it. Okay, it's a universal truth that whenever you take the algebraic sum, there can be changes in the sign, but not in the magnitude. All right. So this particular problem can appear for 6 to 8 marks. Okay, 6 to 8 marks. Okay, there's one more way of asking this particular problem. Okay, and that is something like, let's say, for example, okay, write on the extension part of this particular problem. Okay, first of all, you tell me, did you understand this problem? The method, did you understand?
Yes, sir.
Okay.
Yes,
sir. You have understood.
Yes, sir.
Well and good. Fine. Next, the extension part, you write it. Measure the potential between the nodes. Measure the potential between the nodes B and D. Okay. VBD is equal to how much? And also VDF is equal to how much? Okay, this will make kind of activity from roll number 1 to 30 can find VBD, and from roll number 31 onwards can try finding out VDF. Can you do that?
Yes.
Yeah.
Yes.
And then you can share your answers in the class group, that is C section. I mean, not in the main group, the basic electrical group. Okay, please try to solve it. I will also try to solve. Okay. I will try to solve VDF, okay, because from 30 onwards, not many students are there. That's the reason. Okay. I'll find VDF. I hope you have bought the calculators. If not, please get it as soon as possible.
The 2.4.
All right. You are very fast. Okay, let us check. Just type your answers. You type your answer something like VDF is equal to so much. Okay. Yeah, VDF. Let me just type what I have got. It's taking courage to write it. If it is wrong, don't laugh. VDF is equal to minus 1.5546. This is what I have got VDF as. Okay. Plus or minus is fine, but did anyone get minus 1.5546?
Yes, sir.
Yes, sir.
Okay, great. Great.
Yes, sir.
Fine. So, can anyone tell me what about VBD? Did anyone get it? VBD.
2.38.
Okay, 2.38.
Sir.
Okay, 2.3.
Minus 2.38, sir.
Okay, okay. Minus 2.38, right? Minus 2.38 volts. Okay. How about others? Are you agreeing with these answers? Or is there any calculation error from your side? You want me to show how I have obtained VDF as minus 1.5546?
Yes, sir.
Sir.
Okay, okay. So quickly I will do it. Okay. Others, please bear with me for some more time. DEF, right? This is how I do it. Okay. I just first draw the nodes. Okay. So from D to F, I am supposed to find out, right? So I have to move from node D to E and then E to F. Okay. Since VDF is the unknown potential, normally I will consider it as a battery. Okay, with the unknown potential VDF. Okay, this is how usually I do it. And then I'll connect the nodes between D and E. Okay, what do you have? You have a 0.02 ohm resistor, and between E to F, you have, what do you have? 0.01 ohm resistor. And this is how I am going to apply KVL in this particular network. And let us also mark the currents that you have initially marked, right? So you have marked a current, okay, and the direction of current is what? D to E, right? From D node to E node. Similarly, you have a current flow from node E to node F. Okay, so I'll just place those currents. So you have assumed IDE, you have also assumed IEF in the designated path. And we have found, right, the current value. What is IDE? IDE is negative 91.8. So let me write it here, 91.8. Of course, with a negative sign. Okay, so it is minus 91.82 current IDE. Okay, and current IEF is positive 28.18. So let me write this current as 28.18. Okay, now let us apply KVL. KVL in clockwise direction. Okay, so what do I have? VDF. Okay, then minus 0.02 into the current is minus 91.82. Okay, then minus 0.01 into the current is positive, hence 28.18 is equal to 0, or VDF is equal to minus 1.8364 plus 0.2818. So that gives VDF is equal to minus 1.5546 volts. Okay. So those who did not get the answer, probably you guys can follow this particular method, okay, and apply the same method to find VBD as well. All right, fine. Okay. Next problem. This is from Kulshrestha. Just right. Kulshrestha. Okay. Right now, it's a simple problem. A car radio designed to operate from a 6.3 volt system, from a 6.3 volt system uses 4.5 amperes of current, 4.5 amperes of current as shown in the figure. First part, what resistance R should be placed in series with this radio if it is to be used in a 12.6 volt system. If it is to be used in a 12.6 volt system. Second one.
The 12 point.
Pardon me?
So what is the value of the voltage? 12 point?
12.6.
Okay. Thank you, sir.
So I got the answer for the first one, sir.
Pardon me?
It's 1.4 ohms, sir.
Just a minute. Part B, I'm not done. Yeah, your answer is correct. Okay. Part B also you try to find out. What should be the power rating of the resistance? Power rating of the resistance. Okay, so this is the circuit. Okay, this is your radio. Okay, the terminal voltage they have given 6.3 3 volts. And the operating system voltage is also given. That's 12.6 volts. Okay. So you're supposed to find the value of R as well as power rating of the resistor. The value of R, some of you have already found. Okay. So very simple, you can just apply, the Ohm's law. Okay. So, I mean KVL, right? Because there are more than one voltage source. Apply KVL in the clockwise direction. Okay, let's say this is my current I, and they have given the value of current as well, right? How much is it? 4.5 amperes. So basically this is 12.6 minus 4.5 into R minus 6.3 is equal to 0, or R is equal to 12.6 minus 6.3, that is differential potential, divided by the current. Okay. As your friend mentioned, this value is 1.4 ohms. Okay, that's the first part. Second part is what should be the power rating of the resistance. So power rating of the resistance, so let's say power rating is equal to, power is I square into R, because you know current and you have already you have found the value of resistance as well, right? The current is 4.5, so square it into 1.4. How much you'll get? So roughly 20 plus you should get it.
28.35.
28.35 watts. Okay. So this should be the power rating of the resistance. It's a simple problem. Okay.
So, but power rating, they usually show it with 28.35, comma the voltage, no sir?
Which one? Okay, if that is the
Power
case, yeah,
definition.
what you have to do is you have to find the voltage that appears across this resistor. So either I square into R or V square by R, you'll get the same answer. So this voltage is basically 12.6 minus 6.3. Okay. So some voltage you'll get, right? So that voltage square divided by this resistance value should give you the power rating. Okay. Yeah. All right then. So any problems or any doubts regarding assignment problems? You could solve, right? Those assignment problems.
Yes, sir.
Yeah. So tomorrow I will solve some more problems in KVL. Okay. And then I will give you some problems in practice problems in KVL circuits also. Okay. Fine. That's it for the day. We will meet tomorrow.
Thank you, sir.
Yeah. Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.